Okay, so we're asked to set up continuity and Bernoulli equations for this problem here. So we see there's a hose, 3 centimeter radius, circular cross section here, and then a 1 centimeter nozzle at the end. So we'll apply the continuity equation, and that's going to say the volume rate of flow, which is the ratio of volume to time, is cross-sectional area times speed in the hose, is cross-sectional area times speed at the nozzle. So we see 0.75 liters per second here. That's a volume rate of flow. We need, of course, to convert that to SI units, which is cubic meters per second. And of course, 1 cubic meter is 1,000 liters, so we end up with 3 more powers of 10. It's 7.5 times 10 to the negative 4 cubic meters per second. So that's our volume rate flow. So we'll put that in here. And then we set that equal to area times speed. Well, the area here is pi r squared. 3 centimeters is 0.03 meters. So this equation can be solved to find the speed of the water in the hose. The nozzle is 1 centimeter in radius, so 0.01 meters. And this equation can be solved now to find the speed of the nozzle. So we're just asked to set up the equations, and we've set up the continuity equation. Continuity principle just says that the volume rate of flow at any 2 points along the streamline must be the same. Next, the Bernoulli equation. Bernoulli's law says that the quantity 1/2 rho v squared plus rho gh plus pressure must be a constant along the streamline. So the value inside the hose will equal the value when it exits the nozzle. Now, fluid exposed to the air will be at atmospheric pressure. So coming out of the nozzle here, this will be atmospheric pressure. Coming out of the nozzle, you can make the ground your zero of height, and then this will be 2.5 meters. The speed here, well, you'd have to solve for the continuity equation, but once you solve that, you'll know what that speed is. So we know everything on this side. We'll assume it's water, so that the density of water, if it's fresh water, is 1,000 kilograms per cubic meter. And then on this side, the height's 0, and then this speed will be the speed within the hose that, again, you'll get by solving this continuity equation here. And this pressure is the unknown. So let's substitute in, putting in 1,000 for the density of water. So whatever the hose speed that you get here, you substitute in. Here's the unknown pressure. This term here is just 0, it vanishes. So whatever the nozzle speed was, whatever you get by solving this equation, equal to that, you put it in there. And then this is 1,000 G times 2.5 plus atmospheric pressure. So that equation can be solved for the unknown pressure. And that's how we will apply the continuity principle and Bernoulli principle. Now, unlike in the previous example where we made an approximation, we said that one of the speeds was so small we would just take it to be 0. We won't do that here because you can actually solve this equation for these 2 speeds exactly. So that's how to apply the principle of continuity and Bernoulli.